下一位报告是我们的东道主，我们的重庆大学的黄小旭老师。黄小旭老师大家也都非常熟悉，是他长期从事呢金属材料的塑性变形、微错、晶体学等方面的研究工作。在 Nature Science、P 呢是 Matter 等期刊上呢发表了300多篇论文。黄老师呢，曾经是哈尔滨工业大学获得博士学位后，在丹麦的历史国家实验室工作过。那么现在是重庆大学的教授。好，黄老师，我们准备好了吧？
好，谢谢陈老师的介绍。
好，我们掌声欢迎黄老师给我们做报告。
好，非常高兴啊，有机会在重庆，就是谈我们的工作。然后这是我们第7次的就是材料基因工程论坛。我大概是在绵阳那一次讲过一些我们当时的一些工作。在那之后呢，我们再继续努力，然后进一步发展我们的技术，就是我们关于3维透射电镜技术。今天我要讲的是。就是我们最近的关于3D orientation mapping 的一些发展和它的一些应用。Okay, and probably I will speak because I prepare my slides in English. And probably it's easier for me. So anyway, and I'm going to talk about the 3D orientation mapping and high throughput characterization of structural parameters in polycrystals. And yeah, first, of course, I would like to acknowledge my co-workers, colleagues, and students who made great contribution to the work I'm going to talk. And also, I would like to thank the sponsors, in particular, from NSFC, from the National Key Research and Development Program, this in Chinese 13-15 and 14-15重点研发计划. Those really, and it's because of their support, we can continuously and to do this work for many years, to improve our technique so that we can eventually use the technique for materials research. Here is the outline of my talk, and we start with motivations. Yeah, I'm talking about the polycrystals. Polycrystal, we know, of course, and the polycrystals are composed of many grains and with varying sizes and orientations. Basically, to characterize the polycrystal, really to characterize two things. One is morphology, the other one is crystallography. And the two big categories. And I guess most of you, probably all of you know that nowadays the most very popular technique is EBSD, which is SEM-based and diffraction technique, which can generate the map like on the left side, and it's a very colorful, very nice map, and from which we can get, and the grain size, orientations, the textures, even in some cases the boundary plan. But what we are doing in the real life is the 3D, and in particular for structural materials of polycrystalline materials, and they are in 3D shape. We are using in a bulk shape. Really, the materials properties and the performance really rely on their, the performance, their behavior in 3D, not in 2D. And so we need 2D technique. And in particular, and when we talk about material science, we're trying to establish the correlation between structural parameters and properties. And without complete characterization of the structural parameters, we cannot really establish precise and correlation relationship between structures and the properties. From a 2D technique, in many cases, we cannot get complete characterization. For some of parameters, we cannot really simply obtain from the 2D techniques. For example, here for the polycrystals, the parameters down here list in red, and we cannot simply get it from 2D techniques. We need 3D techniques. And that's also the reason nowadays, when we do the material science, and on the one hand, from the experimental side, we do mostly 2D observations. But on the simulation side, the computational and science, we do a lot of computer simulation, which is in 3D. Exactly like Professor Wang just showed. One hand, we do 3D simulations. On the other hand, but we can only do 2D, but at least most in 2D. So to really develop and to get further understanding of structure property relationship, we need full characterization and of structural parameters, which we have to rely on 3D characterization techniques. And today I'm going to focus on the 3D orientation mapping. In terms of 3D orientation mapping, over the last 2 decades, scientists over the world has spent tremendous effort to develop all kinds of 3D techniques, neutron diffraction-based, synchrone-based, or even the 3D, EBSD, combining EBSD 2D mapping with series sectioning, you can get the 3D. But for the neutron and actually the synchrone-based technique, the main problem for the technique, and they are very cool technique, which already have solved a lot of problems. But the problem with those kind of techniques, the neutron or X-ray based, are the poor resolution. The resolution nowadays available are kind of sub-micrometer scale. But for the EBSD, 3D EBSD, people are not using a lot. One, because the resolution is really depending on how precisely you can fab or polish your samples down, which is normally 20 to 50 nanometers, and also which is a kind of destructive technique. When you complete the series sectioning, your sample is gone, which you cannot do any further. You cannot really follow what's going to happen afterwards. Of course, what we wanted to do is to develop 3D orientation and technique for orientation mapping at the nanoscale, which really try to fill in the missing gap here, and to develop nanoscale resolution 3D orientation technique for studying nanocrystalline materials, which really has been a very hot topic for the last 20, 30 years. And basically that has to be a TM-based technique, transmission electron microscope-based technique. And in this case, we, and for audience here, when you do TM, and the TM samples have, certain thickness. Normally it's a few nanometer to say 100, 200 nanometer. And when we look at the nanocrystalline materials which have a grain size, say 10 nanometer, if you have a sample thickness 100 nanometer, which means there are 10 grains on top of each other, through the sample thickness. That's really the situation like this one. When the electron beam goes through the sample thickness, goes through all the grains, which will generate a very complicated signal. If you want to do diffraction, you get overlapping diffraction patterns. To deconvolute, this superimpose different patterns is not an easy task. But even worse, actually, when you do the nano diffraction, because when you try to get a nano diffraction signal from nano grains, you have to do nano beam diffraction. When you do nano beam, convergent beam diffraction, your sample will be very quickly damaged. So that's seems directly using diffraction and the idea doesn't work. And we developed a technique using dark field imaging. Because dark field images contains both image information also, and which directly correlate with the reciprocal space. There's orientation information there. Anyway, we developed the technique, and based on the development, both software and hardware, we were able to transform a traditional conventional transformation electron microscope into a microscope which allow you to do 3D characterization. Anyway, we spend a lot of, great effort to develop software for alignment, for denoising the noise, and also try to, of course, most important, try to get the orientation or diffraction signal information to assign orientations to each pixel and on the images. Anyway, after many years effort, and we developed the principle, improved the technique. Nowadays, the techniques is ready for use. And actually, we developed this technique, which has a resolution 1 nanometer, and we can map a volume at, say, 500 cubic nanometer and size. And yeah, here just here's one slide in Chinese, just give an overview what we can do by using the technique. And here the 3D orientation, the grain mapping in 3D. Of course, we can, for the grains or face, we can get the shape, size, position, and orientation. Also, there are spatial distribution where they are in the volume. And also for the boundaries, for the interfaces, we know the orientation relationship between grains, misorientations, also the normal to the boundaries, also curvature or the type of boundaries, and also there are spatial distributions. Also, and at the same time, we develop another kind of technique is for mapping the 3D structure of the most important lattice defects, which is dislocations. And anyway, that's in this case, of course, our aim was not only get the 3D image of the dislocation structures. We want to get all information associated with the dislocations, their shape, their crystallographic and characteristics. For example, the Brooks vectors, line directions, and also, for example, if a dislocation loop, where they are, which kind of crystallographic plans, and so on. All the really, our technique is really kind of a dislocation. It's kind of a tomographic crystallography of dislocations. And based on the tomographic technique, we can quantify, it means all the crystallographic and the parameters related to the dislocations. Yeah, it gets back to the orientation mapping. And for example, here, just give a couple of examples. Here again, there's gold nanoparticles and the deposit on the carbon film. And in this case, in this volume, in this area, we have more than 7,000 grains, and which are either isolated grains or, several grains from one gold particle island. And yeah, in this case, the average grain size is about 8 micron, and the smallest we can see was 2.5 micron. And yeah, and here when we get the map, we can also characterize all the boundary and misorientation and boundary plan, and there are normals, and all that's 5 parameters and associated with the boundaries we can quantify. Also based on this and 3D map, we can quantify all them. Also, of course, for curvature, and to do a curvature study, we have to use a 3D. And here are just examples for just to pick up one of the particle which contains several grains separated by different boundaries. In this case, they are sigma 3, sigma 9 boundaries. Anyway, we can simply analyze this. And anyway, altogether we can really characterize all the 5 parameters, for the grain boundaries. Of course, based on that, we can analyze, you can dig into the science. And actually, that's just a small paper by my former PhD student, actually based on this work. And he got, this work was published in 2022, and he got, this year in July, it was announced he got this ACT Student Award. And this year, and in total, there were 14 students who got the work. He was one of them. Here is another example of 3D mapping for deformation-induced nanostructures. In this case, here is a deformed and aluminum, and actually, really from the surface nano grains, we get the sample from the surface and try to map out the nanostructures. In this case, the structure is more elongate, but the point here is in this deformed structure, which contains relatively high density of dislocations. Even for those samples, all technique can work. You can get the orientation map. Again, you can analyze the grain shape, size, boundary misorientation, boundary plan, all information you can get. Yeah. Here is another example, and to look at the grain growth for nanocrystalline nickel and in 3D, and we map out the grain, all the grains, the films. Actually, here is the thin film, and before and after annealing treatment to see how the grain become bigger, how the grain growth taking place, and again. We can, for all the grains, we do the similar analysis and boundary plan misorientation, boundary plan normal, all kinds of parameters, and then try to understand. When we have the misorientation, boundary normal, you can calculate the boundary energy. Anyway, we want to understand why some grains suddenly grow abnormally, grow much bigger than the rest, and based on those. Complete information, we can definitely get much better understanding what's going on during this annealing process. Actually, this morning, we announced the new journal by Professor Xie, the new materials engineering advances journal. This work was just submitted to that journal, was accepted for publication in that journal. So that's just a kind of mapping. And I mean, go through quite quickly. We have one more example to show. And so that's that's just static and the 3D orientation mapping. Now we want to go further, try to see the evolution. I just show one example to show the kneading process, the grain growth. But here we do some deformation. It's more challenging in the TM. And here really the 3D orientation mapping plus in situ mechanical testing. Here we use a compression test in the TM. On the left side is really the initial sample and after deformation. Actually the sample tip, the top part, and has really squeezed very much and deformed too much. We can really follow the details. So we analyze, the sample below we only analyze the volume from, the down part. and ignore the tip part. Anyway, that's in situ TM deformation and together with a 3D orientation mapping. For this one, and for this part, the deformation is roughly and 5%. They're not completely uniform because there's a tip angle along the sample height. And anyway, the strain and the compression strain is rather, the range is pretty narrow, around 5% and on average. And the size, actually, here, the size of the grains will measure from the volume, not from a 2D projection, which used to, for nano studies, people use dark field images to get the grain size. Actually, when we compare the grain size measured from 3D volumes, and which is very different from what we get only from the 2D images. And yeah, anyway, in this case, the grain size is around 20 micron, and the grain size doesn't change much, of course, because the strain and strain level was only 5%. And anyway, the important things here, we map all the grains in the volume. We follow every individual grains to see how their orientation changed and before and after deformation. Here are the results, actually. And here is before, here is after. And again, we just compare each grain before and after deformation. And yeah, that's, of course, the main things, the motivation for us to do this study, to see whether we can, from the rotation or orientation change information, to get some understanding what's going on or deformation mechanisms, and for this nano-creation, the nickel sample. And anyway, we found here is just the compression axis. This really this principal axis change is really characteristic and information we should follow to understand what's going on. And actually, in this triangle, the size of the spots indicates the rotation magnitude, 1 degree or 0 degree even, and up to 8 degree. The big size means a big rotation angle. Yeah, and seems the magnitudes of rotation has nothing to do with orientation at all. It's pretty random in the big and the small dots, in this triangle. And this is, when we first look at this, such data, we were surprised why that can be. And of course, one explanation is, the grain boundary sliding or all kinds of grain boundary medial process has occurred, which give you such kind of random kind of and orientation change. But, and here is, the just before after, deformation, we see a kind of random orientation change. And of course we do, and the crystal plasticity modeling to see if we, based on initial orientation, where the individual grain, where they should rotate to. And what we found is, if we compare the experimental data with the prediction, and we found roughly and about half of the grain, and half you can somehow find a correlation between the experimental observation and the prediction. But the other half, they don't. They are crazy. And even some of them rotate back. Yeah, the comparison test, so the crystal is supposed to rotate downward, but many of them rotate upward. Why that can happen? How this can happen? And we look back our movie, and during this movie recorded during the compression test. And the first row is during loading. For example, look at this one is of here loading and then this is unloading. Seems loading, unloading all the way, they're all white, which means they are under different condition. And seems nothing has really changed and for them. But if we look the location here, number 2, here's kind of dark and contrast gradually become bright. When you do unloading, they become to be darker again. Something happened during the unloading process. During the unloading, some of the crystal, they rotate back. Surprisingly, we know the plastic deformation cannot recover. But this one shows, yes, some of the grains they did. Here just another test. We did many times, repeat and test to verify what we have observed. And here just a movie try to look at the local intensity change. Anyway, that's a very probably not easy to see what is really, maybe here can be a little more clear. For example, here from here to here is all the way loading. Here is the holding process, during the holding, and here is unloading. Anyway, during the loading process, if the intensity change means orientation change, and during the loading process, of course, the crystal rotation will occur, and it all changes different way. It's not. They should, that should be. That's something we should observe. And during this holding process, of course, nothing really happened. But during this unloading process, you see this one, the purple one, this gold one, this blue one, they all decrease their intensity. Anyway, we do see and the intensity change during this unloading process. After removing the load, the stress, the crystal still can rotate. Why? And actually we did this, and in the TM we do this loading process, try to see whether this loading and unloading they form, and they are whether they overlap or not, or they form this loop. But we observe the loop. Oh, must be some so-called backstress or generated during the deformation process. And then we quantify the backstress. We found the backstress during this tiny sample deformation. Although there's kind of bulk 3D shape, but that's really small. But anyway, the point here is the backstress built up to 2 gigapascal, very high actually. And what does this mean? First, we observed from within the TM high resolution, we see full dislocation, partial dislocation. And this, anyway, in TM, probably is not something difficult for you to see this. But when we analyze, and why the dislocation can activate. And so that's anyway, we have the grain size from 10 to 80 nanometers. And from theory, we know for nickel and around 20 nanometers, the activated dislocation will switch from full dislocations in the coarser grain size into partial dislocation in the final grain sizes, final grains. And so, based on, anyway, it's a very simple analysis. We analyze. We know the orientation for each grain. We can analyze the Schmidt factors, and then try to see whether the backstress can big enough to generate some moving back of dislocation, which give you the reverse rotation of the crystals. Anyway, we define one parameter, R value. R just simply mean if when R is larger than 1, dislocation activity and will occur, and basically dislocation sleep, and will occur, and and when R less than 1, nothing will happen. No dislocation sleep. And of course, during the loading process, which is the left side, basically all the grains are deforming by dislocation sleep. And surprisingly, during the unloading process, based on the mirror backstress, we found almost half of the grains have R value larger than 1, which means in those grains, the dislocation activity can occur, which really the backstress can drive the dislocations back, and in the opposite directions. Even more surprising, and what we see is, and the grains which behave strangely, give you, from which we see the reverse rotation are the larger grains. Of course, from back stress generation point of view, it's very nature. Anyway, it is this kind of, it makes sense. It's kind of consistent, and that's what we believe. This for nanograins, and the crystal and may rotate back after plastic deformation, because generation of high back stress, and also, and this, this high stress generation require, of course, because the constraint between grains. If we do the 2D observations, you won't see this kind of, at least the constraint will be very much released. You won't see this very high back stress generation. Of course, you won't see any rotation, reverse rotation. And that's really mean the 3D characterization is essential for us to really understand what's going on during the plastic deformation of nanocrystalline materials. Yeah, also, though our grains vary, the grain size vary between, say, 10 to 18 nanometers, and but it's surprisingly the deformation is so heterogeneous. Of course, the soft grain, the hard grain, they deform differently. Of course, as a result, it generates back stress, which gives the phenomenon we observe. Yeah, it's very much what I'm going to talk today. And to summarize, I want to say we have developed this 3D technique, and for very fast, what we call, I would try to say the 3D technique is kind of a high throughput technique, because from one experiment, from one data, you can get all parameters, a lot of parameters, and 1,000 parameters quantified. And also the 3D technique gives us a new chance, to look at some new or old and phenomena. And what's the next? And of course, we want to go from 3D to 4D to have a time resolution and included. That's what we are doing. And actually, we have made some progress. For example, in the dislocation tomography, we can do a 3D mapping within 2 minutes. Right, 2 minutes we can do a 3D mapping. We can really follow what's going on, how the dislocation structure evolved, in 3D. Yeah, that's what we are doing. I hope maybe next time we can report something on 4D studies. Yeah, thank you very much.
好，非常感谢黄老师的报告。我们那个黄老师的报告和与前面的我们的王老师的报告形成了非常好的一个呼应关系啊。前面是在用计算的方法来展示或者是预测微结构的演化。我们黄老师的报告这是从实验的角度来展示，精确的展示3D 的这个微结构。我相信一会儿我们也许我们在后面的这个交流过程当中有更多的问题会向我们2位老师请教。好，我们再一次感谢黄教授的报告。